Hello students, welcome back to another lecture in our course Environmental Modeling and Simulation. In today's lecture, we will draw face portraits of 1D models using R. Remember, R is a freely available open source statistical software and also a powerful data visualization platform. And since it is freely available, I definitely want to show you how to make face portrait using R. We are going to start with 1D models. The first model that we are going to investigate using R, we are going to make a face portrait, we are going to make the flow lines, is the logistic growth curve. If you remember logistic growth curve, it looks something like this. dn by dt, where n is the variable that is increasing, that is growing over time or decreasing depending on n naught, is equal to Rn 1 minus n by k. R is basically the growth rate and k is the carrying capacity. And when we drew the face portrait graphically, what we did was we found out the fixed points, which is when dn by dt is equal to 0. In this case, that will be when n is equal to 0 and n is equal to k. And then after drawing the face portrait, we were able to draw the flow lines of how n will change, how dn by dt will change with time. The second model that we are going to look at today is Gumpert's growth model. And the example that I gave in the class for Gumpert's model was tumor growth. Tumor growth is fascinating for many reasons. The first is that the tumor tends to undergo a decay of growth rate as it grows in size. Basically, the more tumor cells there are, the slower the overall growth rate would be. And in the class, we discussed that the most probable reason for this is because the immune system starts controlling it. The other reason is as the tumor grows, so when the tumor is small, it is able to receive nutrients from the body and continue growing. But as the tumor becomes big, only the cells near the surface of the tumor are able to receive the nutrients and continue growing, while the cells on the interior of the tumor, they start undergoing necrosis because they are not getting the nutrients they need. So unlike logistic growth curve, where we first have what seems like an exponential growth at the beginning, or when n is sufficiently small compared to k, followed by what appears to be a linear growth, and then the characteristic S equation, the logistic growth as n approaches k. In contrast to that, the Gompertz model, even though it also appears to have a S-shaped curve, in Gompertz model what happens is that the growth rate, which is dn by dt, undergoes exponential decay. The equation for Gompertz model, as we discussed in our class, is given by dn by dt is equal to minus an log bn, where as we discussed, b is 1 by k, where k is the carrying capacity. In this case, it is the number of cells in the full size tumor. So we are going to model these two, we are going to make face portraits for these two, we are going to see the flow lines. The important thing is that once we have a face portrait, or in this case we have dn by dt plotted against n, and we have the flow lines, we know how n is going to change as it approaches a certain value, or depending upon the initial n naught. So let's get started without any ado. We are going to use R, and there is a particular package in R called Face R. We are going to install this package. I'm also going to walk you through the different options that are available in Face R, because not only can you draw flow lines using this package, but you can also draw null lines and face portrait. Possibilities are nearly endless. All right, let's get started. Okay students, so this is the screen of R Studio. Remember, the R Studio is GUI for R. There are other GUIs that are available for R. Here GUI means graphical user interface, which makes it easy for us to use the R software. RStudio is also open source and freely available just like R, and it makes it really easy to install packages and to change the working directory. For example, in the previous class on R, I showed you how to choose the directory path that you are using, the working directory path, and how to check it. Here you can just go to session and you can set the working directory, choose the directory you want. Also, it's easier to save the graphs here that we make and select their resolution than doing it by command line using R alone. So I highly recommend that you give a try to RStudio if you're using R. Okay, so we are going to first draw the face portrait, the flow lines, the flow field actually, that's the right word, for Logistic model. And to do that, first we have to install a package called phase R. Okay, so before I do that, let me start a new script file. So for that, you can go to the first icon here, which is a plus sign, click on the arrow next to it, and then our script. So we are going to write the script. So the first step is install the package phase R. So how do we install it? Through command line, it's install.packages, and then we have phase R. The other option is to actually use the icons here, and you can install packages by going into tool and then clicking on install packages. Since I'm more used to working with command line, you will see that I'll be using the graphical user interface, but also relying heavily on command line to make or do things that we needed to do. Okay, so here there is an error in install.packages. It says phase R is not found. Let's try again. So now R is installing phase R. You need to be connected to internet for installing packages. If you're not connected to internet, then the other option is to download the package when you are connected to internet and then install it by asking R to use the downloaded file. And that you can do very easily by going into tools and then installing packages. Now I have put a comment sign in front of install packages because I don't need to run this command again. Once you have installed a package, R remembers to use it. So step one would be to tell R that we are going to use the package we just installed, which is phase R. This is the step one. And to run the command, you can always click on the run here. Okay, now we are going to define a function. So let me write a comment here. So let's call this function Logistic. In the previous class where we used R to make a very simple diagram, we used the function command to define a function. In the function, there are three inputs. One is t, which is for time. Then there is n, which is the variable that's changing. And then parameters, which are the parameters in our logistic model. The next step is to put the curly brackets in. And then here we are going to write a model. And since this is a one-dimensional model, it's going to be very easy to write this one. So we say list, and then here we write our model. And our model is parameter 1. So this is the first parameter. Remember, parameters is going to be a list of parameters. Since this is logistic growth model, there are going to be two parameters here. So list parameter 1 into n, which is the number of organisms that we are modeling, into 1 minus n divided by parameters 2, which is the second parameter. This is your logistic growth curve. And now we are going to use phase R package to make the flow field. Okay. So Notice here that I changed the name of the model from Logistic to Logistic EMS, and the reason for that is Logistic is a model within the package phase R, and I want to be clear that I am talking about the Logistic model that I am defining for our course Environmental Modeling and Simulation. Okay, now let us use the phase R. The command in the phase R to make the flow field is known as flow field. Now using phase R you can make null clients, phase portrait, you can do a lot when it comes to ODEs, but we are going to make the flow field. So let us call this Logistic EMS flow field. You can of course choose simpler names. I like to choose names that are obvious. The command is flow field, and look here, the R tells me what flow field is. It is a command in the package phase R. So you see here the package's name comes here, and then in the yellow box here the R is telling me what inputs flow field requires. First it requires the model, then it requires xlim and ylim, which is a way to limit the range of x-axis and y-axis. Then it requires the parameters, which in our case would be a list of two parameters, parameter 1 and parameter 2. And then it requires other information. This is very important information here, which is required by flow field, which is system. So in the example in the yellow box is 2.dim, which is 2-dimensional, but actually this is a 1-dimensional model, so we are going to write 1.dim. And then there is more information regarding points, color, arrow type, arrow head. All these information you can look up online. For example, what kind of arrowheads are present, what size arrowheads, how they look like, and what colors are present in R that you can use. Okay, so let us write down our flow field command. Our model is the first thing that we tell flow field. Our model is called Logistic _ EMS, comma. Next information is x limit. So let us say x limit is from 0 to 4. We can always vary x limit and y limit. Y lim is, let us start from a negative number, that would be fun, -1 to 4, comma. The parameters, very important, the list of parameters, we are going to have 2 of them. So let us say the growth rate R is 0.8, and then the K is 2 units. Now we are going to tell phase R that our system that we are dealing with is a 1-dimensional system, so 1.dim. And then we are going to say there is no need to add other plots to it, so add is equal to false. Now with false and true, you can write just the first alphabet in capital letters, or you can write the whole word in capital letters. Okay, so this is our code, let us run it. Now remember that for R, you can run the code one line by line, like we did when we were installing our package and then we were telling R that we need to use the library phase R. Or you can select the lines that you are interested in running as a group and then click on the run button. Okay, so now our environment has Logistic EMS function. This is our Logistic EMS function. And now let us plot the flow field. So I am just going to select this code and then run it. Okay. So notice that the space for the figure is very small, so you can drag the boundaries here like so, and then like so, and then take a look. So this is our flow field for the logistic growth, where the parameters are R is equal to 0.8, which is the first parameter. The second parameter K is equal to 2. So you see, when we start at 2, the flow lines are horizontal, which means the flow lines are telling us that 2 and 0, where the flow lines are again horizontal, are the 2 fixed points. Now this graph is a little hard to read, so what I am going to do is I am going to vary the x and y limit. I am going to make the x limit 2. I am going to play around with y limit 2. So x limit, let us make it 0 to 2. And y limit we can make -1 to 3, not 43. and then run it again. This must be slightly easier to look at. Okay, so this is our face portrait. You see 0 and 2 give you straight lines, and then -1 is decaying downwards, and 3, which is bigger than the k value, is slowly approaching the fixed point 2. If we increase 3 back to 4, I believe we'll be able to see how dramatic the decrease can be when n naught is bigger than k. Okay. So here you see, when we start with 4, there is a dramatic decrease. These vectors, arrows that you're seeing are the vectors, they're the slope field. The direction tells me the direction of flow, and the size tells me how fast the flow is happening. Let's increase it to a very big number. Okay. So you see the flow lines here are quite dramatic because n naught is much bigger than k. Okay, now let's write the Gompertz model. This is our logistic model. Time to write the Gompertz model. The example I gave in the class is that of tumor growth, and I explained to you at the beginning of this lecture why Gompertz model is important. It shows exponential decay of the growth rate. So for that, we have to first define the model. So let's call it Gompertz. Notice that R is not giving me advice on what Gompertz commands or models are available. So this seems to be a unique name. So I'm going to stick with this. And then first thing is we are defining the function. So when R gives you advice, like when I started typing FUN, R said, hey, are you talking about function? Then I can always scroll down to the right command and then press enter, or I can select using my mouse. Of course, then the input would be time, n, and parameters, which again is going to be a list of 2 numbers. Now let's use the curly bracket and very similar. Okay, no. Remember, Gompertz model looks like this. I find it that I need to write down the model in the way I write it in my copy when I'm mathematically solving, to make sure that I don't make mistakes when I'm putting the model here in R. So -1 into parameters 1, take the first parameter as A, multiply it with n, multiply that with log. Since we dealt with rate of growth and carrying capacity, I'm going to stick with n by k instead of bn. Okay, so this is our Gompertz growth model. Now we are going to write a command for phase R to make its flow field. Phase R is an amazing package. You can make null lines and so much more. Remember, with flow field, I need to first tell it what model I'm using. So this is the beauty of RStudio. It will tell you what inputs are required, and R will always advise you, do you mean Gompertz flow field or do you mean Gumpert? So I can always make sure that I'm not making spelling mistakes and I'm referring to the right command, the right location. Next is to define the X lim, which let's stick with the parameters. We can just copy it from here. We can stick with the parameters that we used and then edit it as needed. Okay, and then we can run this. So first we can run all of this together. So let's select the whole code and then press the run. There's an unexpected error in system one dim add false false. Okay, so this is the beauty. Apparently, when I was copying and pasting, I made an error. There is an unexpected parenthesis, a closed parenthesis after add equal to false. So R is telling me that there's an error. So what I can do is I can go back to my code. Now here's the thing. When I am right after a parenthesis, in this case a closed parenthesis, R will show where its relevant open parenthesis is. So clearly the second parenthesis is unnecessary one. Okay, now let's run this. So I'm getting another error which says cannot find the function ln. So if you look here, I use the function ln. By default, R does not identify ln as natural log. But if I write log, it will define. If I want log 10 base, then I need to use log 10. So here is the type, a mistake, a syntax error that I made, and now we are correcting it. Notice it's telling me there are other errors that are made, and the errors are NaNs are produced when I do log n divided by parameter 2. So let's take a look at it. We need to correct this and then rerun. Okay, the mistake was the y was negative. Now when y is negative, I'm saying that there's a possibility of n being negative. Now if n becomes negative, the inside of log n by k becomes negative, and negative of logarithmic number does not exist. So that was the error. So I had to, remember I told you that we are copying the parameters we use for logistic growth. And these are the edits that we need to make when we are trying to figure out how Gompertz model flow field will look like. So now we have a diagram. These errors are very important. I hope they are a good lesson for you. And this is our Gompertz flow diagram. You can see how the flow lines look like. Alright students, so this is all for our today's lecture. We drew flow field or slope line or slope field or trajectories, all possible trajectories for two one-dimensional models, Logistic and Gompertz. When we were running the command for Gompertz model, we learned that the same parameters which worked for logistic growth curve will not work for Gompertz because Gompertz has log n by k, so n cannot be negative and has to be positive, which is not a limitation in the logistic model. Thank you students. See you in the next lecture when we'll work around with 2D models.